Alright, welcome to a video about measurement. In physics, or in any science course that you take, measurement is one of your key ways of getting data. So you need to understand what your measurements mean, what sort of errors are already built in, those sorts of things, okay? The book, just a reminder that these videos are meant to be a supplement to the book, not a replacement for it. It doesn't cover everything. It usually focuses on one part where either the book doesn't seem to get into enough detail or it's just a more complicated part in an effort to help you understand it better. Okay? So, big thing we're going to focus on in here is accuracy and precision, and noting the difference between the two, because oftentimes these words are used interchangeably, but that's not always correct. So, first thing is you need to know that everything has a true value, okay? True value is something that is accepted as the actual value, right? So if you think about it, we have, hopefully you know this, but the boiling point of water is 100 degrees Celsius, or if it's in Fahrenheit, it's 212 degrees Fahrenheit. Other accepted values like pi in 3.14 is not the accepted or true value, but if you continued it out a certain number of decimals, there's also like the speed of light has an accepted value. Any constant that you've ever had, like those of you who've had chemistry, Avogadro's number, okay? So all of those things are theoretical or accepted values that if you are taking a measurement, you should be getting that or something very, very closely to it. Okay, so true values correspond to accuracy. So if something is being measured accurately, it should give you a value very close to its accepted or true value. All right, so if you are measuring boiling point of water accurately, you should be really close to 100 degrees Celsius. All right, so an example of, say you have two measurements, and one of them you get 99 degrees Celsius, and the other one you get 95. Which one's more accurate? Obviously the one closer to 100. Alright? So accuracy is just related to how close to your accepted, your theoretical, your true value your measurement is. Alright? Whereas precision is related to the tool that you're using to measure. Okay? And it's how closely or how far apart your measurements can be. It's usually related to the scale on your measurement tool. All right? So if you think about it, let's say we have this ruler, and it measures from this being 0. Oops, sorry, I'm not writing in here. 0. And then this tick being 10. Those of you that have had chemistry already, you should kind of remember this from the blue, red, yellow rulers. All right, and then let's say we also have this ruler where we have the tick mark here being 0, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tick marks, and now we have smaller increments. All right. So this ruler that has smaller increments that we can measure with is more precise. All right? The smaller the increments of measurement, the more precise the tool is. Okay? So in terms of, say, our boiling point thing, we had the 99 degrees Celsius, right, which was the more accurate measurement. But what's even better is if we can get a tool that is accurate and incredibly precise. So let's say we're getting 99.97 degrees. All right? This tool and this tool are both very accurate. They're both very close to 100 degrees Celsius. However, you can tell that this tool with the decimal points gets us even closer, because it has more precision. We can tell that we're at 99.97 instead of, say, here, we don't know if we're at 99.0 or if we're really close to 100 and it just hasn't rounded up yet. Okay? So accuracy is how close you are to the accepted value. Precision is essentially how many decimal points you can measure to. Okay? So another kind of visual for this, something that's accurate and precise, you'll have really close measurements. The arrows aren't very far apart, and they're at the bullseye, which means they're accurate. all right? You can have tools that are very precise, so you know you're measuring to decimal points, but say you're using it wrong, or the tool just wasn't made correctly, like say somehow a ruler ended up getting shrunk for some reason, like it got printed on the ruler incorrectly, all right? You could have a very precise measuring tool, but it could have some inherent inaccuracy built into it, all right? And then this is an example of something. We got nothing in the bullseye, and our measurements are really far apart from each other, okay? So that's not accurate or precise. You really want tools that fall in this range, okay? So when you take measurements, there's always going to be some variation in the reading. If you took a ruler and measured this line, and all, 33 of us in the classroom did that, we'd probably have 33 slightly different measurements, all right? Or we'd at least definitely have a range, because, say, and this is just an approximation, but let's say I say this is 10.12 centimeters. Someone else might say it's 10.13. Someone else might say it's 10.11. All right, we might even get some 10.0s and like 10.14s. All right, so there's always going to be some variation. And what's happening, if you notice, for the most part, sorry, that should be a 1. If you notice, all of these 1s are the same. It's this last digit that is changing. All right, so every measurement you do should have one uncertain digit, something you are estimating. So if you think about your ruler, if it has tick marks at each centimeter, so here's 0, 1, 2, 3, 4, and the line you're measuring is right here, you shouldn't be telling me that this is 2 centimeters long. You should be telling me it's 2 and then estimating that last digit. All right, I might say it's 2.5, you might say it's 2.4, someone else might say it's 2.6, okay? But that last digit, where it falls between the 2 and the 3, should be estimated. All right, and that gives you something called certainty. All right, so uncertainty is very closely tied to the precision of the tool, because your uncertainty comes from that estimated digit. All right, so the uncertainty is your estimation. So every single measurement that you have is going to have a certain level of uncertainty. And uncertainty can come from more than just the tool, okay? Right, uncertainty guaranteed has to come a little bit from the tool, your estimated digit, but it can also come from how you measure, right? So say we're measuring just a solid line. Let me get my pen going. A solid line. Most likely the only uncertainty in that is going to be your tool, all right? So let's say we have 10.19 as our measurement here. So what decimal point does your uncertainty lie in right here? I'm hoping you're saying the 100th or the 9. All right, so your uncertainty for this measurement most likely be plus or minus 0.01. All right, but now let's say we're measuring a moving distance. All right, we want to know how far in 1 second a car travels, from point A to point B. We want to know how far point B is from the start in 1 second after the car starts moving. Now, this becomes a little bit trickier because you have to kind of estimate your uncertainty. All right, so let's say that this is how far the car traveled in 1 second. Now, are you 100% confident that the only thing that is preventing your precision of accuracy of measurement being just the tool and that estimated digit? Or could there also be maybe you might have stopped your stopwatch in the measurement maybe 1/10 of a second late, or you are eyeballing kind of where it was at that time, so maybe you're off by 0.5 centimeter or something like that. All right, so you have to make sure that you're going to have at least the uncertainty of your tool. All right, and that's this much. But depending on your experiment and how carefully you're measuring things, you might feel you need to increase it. All right, so say you're doing a really, really careful job, but you know that there is going to be a little bit of whether or not you hit 1 second right on the dot, or if you eyeballed the place on the floor exactly where the car was. So maybe you'll say going to go with, plus or minus 0.5 centimeters. All right? And even still, that might be a really gracious amount of uncertainty. All right? But all of these numbers, whether you're doing very, very careful measurement and the only thing you have to worry about is your tool, or if you're in a situation where your measurement is a little bit more difficult, these all relate to a percent uncertainty. And the book talks about this, and it kind of shows you how to figure it out, but I will do a calculation for you just so you are aware. All right? So let's make this guy a little smaller. Move this over, and we're going to figure out a percent uncertainty of these two possibilities. All right, so say we are only off by the uncertainty of our tool. In order to figure out the percent uncertainty, you take your uncertainty, the 0.1, and then you divide it by your actual measurement. And you said it was 10.19. So we have 0.01 divided by 10.9, all right? And then remember, whenever you are doing percents, you multiply by 100 to get your final answer, all right? So times 100 equals, that gives you a 0.09% uncertainty. This is a very, very small amount of uncertainty, and most of us probably aren't that good at measuring things. All right, so let's see. I'm sorry, I just typed that in there wrong. Let's try our still somewhat gracious but higher level of uncertainty, the 0.5 centimeters divided by 10.19, then multiply that by 100. All right, so 0.5 divided by 10.19, and times 100, and that gives you a 4.9% uncertainty. All right, this is more within the realm of reality, and maybe even a little higher than that when we're actually doing labs. All right, so more often than not, you will need to add some estimated uncertainty in there for it to be more realistic. We'll get into that in more detail as we start getting into labs, but just so you're familiar with this idea and how to calculate your percent uncertainty. But that's the end of the video. I hope you took some notes. Feel free to reference this again later and bring questions to class.